So I've worked out the first one with a few friends. Do you want to do this one, or I mean, I guess it doesn't matter. You haven't seen any of these anyways. So um, let's start on this one because I think feel like this. You know what? Let's do this one. It's a good problem. I think we would
Okay.
benefit from it. Okay, so this is what we recently learned. Chandana, feel free to answer the questions as well, um, and if you get stuff, we can always work it out. So a loudspeaker is emitting sound waves towards an open end. So we can see that this is a closed pipe, right? Because it has one side that's closed and one side that's open. That means that this here is going to be a node. We already know that, right? Because it's fixed. And this, the open end is going to be an antinode. You're going to have a higher or low over there. Okay. Now, there's a standing wave that's formed, which is important, and you have the displacement of molecules in air. Okay, so here's a loudspeaker. Now you see that X and Y are equilibrium positions, and the arrow represents the velocity of the molecule at Y. So we can see that if the wave is to the bottom, right? The wave is to the bottom of the equilibrium, that means displacement to the left, which means the velocity of Y is to the left. Okay, so that makes sense. Okay, now this loudspeaker emits a sound towards an air-water boundary, and A, B, and C are parallel wave fronts emitted by the sound speaker. So these are wave fronts. So that means the ray is parallel to the wavefront. This is the ray. The arrow that they've drawn is the ray itself. Okay. Now the parts of wavefronts A and B are in water are not shown, and wavefront C has not yet entered the water. Okay. So now outline how a standing wave is formed. So remember, in IB you can do bullet points. So how would we? Okay, CJ's here. Okay. All right. So how can we say a standing wave is formed? This doesn't even have to do with the question. It's more of like a basic, just to get yourself started. You can do bullet points. What's the first thing? CJ, Chandana, you guys can respond, or I can. Anyway. You have an incident wave, right? You have an incident wave that's going with a particular speed. Incident wave is reflected, and then that wave is reflected back, producing a wave with the same speed in the opposite direction. That's the key part. You have an incident wave that's reflected back, and that reflected back is producing a wave with the same speed in the opposite direction. Interference and superposition result in points of maximum interference, which is, or I should say maximum interference. I should say points of maximum displacement, which would be what? You have maximum?
Antinodes.
Yep, antinodes. Yep, exactly, antinodes. And points of minimum displacement, which are nodes. Okay. Is there anything else we would want to add to this answer? Incident wave is reflected back, producing a wave with the same speed in the opposite direction. And then interference and superposition result in points of maximum displacement and points of minimum displacement. And one more thing. If we really wanted to get a good answer, I think we could also mention here that this is the maximum is constructive interference. This is constructive right here. And then the minimum displacement is destructive interference, right? Okay, let's look at the mark scheme and see what they say. The independent incident wave from the speaker. Yeah, I guess you don't have to mention from the speaker, but in this case, I think it would be beneficial. So next time I would be more specific maybe. The incident wave from the speaker is reflected back from this closed end. And because they superimpose or combine or interfere, whatever you want to say, that will earn you 1 mark. So in fact, for this question, you don't even need to mention the constructive destructive part. But I've seen other questions where you do in order to get the point. So, no need to write complete sentences. Just keep it straight to the point and make sure you understand the definitions of vocabulary. Okay? All right. Now, Draw an arrow on the diagram to represent the direction of the motion of molecule at x. So CJ, here's a diagram that we looked at. So here's a loudspeaker, and it's a standing wave that's formed. It's a closed instrument. So at x is the velocity is. It says draw an arrow to show the velocity of x. Is it velocity or displacement? Either way, it'll be the same direction. Direction of motion. Okay. So which way is x going to go? Is it going to go to the left or to the right? So let's look at this. Y, they've told us is going to the left, and they've shown us that if it's below, and they've shown us that this line right here, that's the equilibrium line. So if it's below the equilibrium line, they've told us that it's displacement to the left. If it's above, it's displacement to the right. So if I have x here and this line is above, is x going to the left or to the right?
It would be going to the right.
Yep, to the right, because it's, so you would just draw your arrow like that, because the standing wave, remember, this is sound, right? Sound is a longitudinal wave. The way these particles are not actually moving up and down. That would be a transverse wave. This is a longitudinal wave because it's compressions and rarefactions, right? It's just that we draw it like a transverse wave to help. It's not really a transverse wave, but we draw it like that to help us visualize. So that's why we're using it. Okay. Mark scheme, let's see, horizontal arrow from x to the right. Perfect. Okay. Now label a position n that is a node of the standing wave. So there are 2 points on here that we could label. What are those 2 points? You guys can try and annotate on the screen as well if you'd like. If you're on a device that will support that. So one we already talked about, right, Chandana?
Yeah, I think.
It's just by definition. So so we know that whenever there's a fixed n, that's going to be a node, right? Because it can't move.
Yeah.
So that means this here has to be a node. So you can label that with an n, or where's another point you can label with an n?
The other, wait, this one here, or maybe.
Yep, yeah, that's perfect. So you would write an n there. That's perfectly right, because a node is just a point that's in the equilibrium that's not going to move up and down. Because what's going to happen is it's going to go like this, this, and these nodes are going to stay still. That's the whole point. Okay, good. Yeah, they drew it over here. Either way is fine. Okay, now it says the speed of sound is 340 meters per second, and the length is, okay, so let's write these numbers down. V is 340 meters per second, okay? And then the length of the pipe is 0.30 meters. We need to find the frequency. Now, how do you reckon we would do that? What do you think? Whenever you're doing waves, a key rule, just a general, go ahead, CJ, go ahead.
I was gonna say, couldn't we use like the fundamental frequency thing? Yes,
we're gonna have to eventually use that, but I think a good starting point is V equals lambda f. If you start off here, that's that golden rule of that golden equation in physics in waves. It's always comes in handy whenever you're doing calculations like this. So what this tells you is that f is going to be V over lambda. Now, CJ, how do we find? They gave us V. How do we find lambda? That's the question. How do you find lambda? So
now we use the
yeah.
Now we use the frequency things. Okay.
Yes. So in this case, whenever you're doing these types of problems with lambdas, it's easier just to visualize it. Instead of memorizing that formula, I really don't think that formula helps. I mean, it is useful, don't get me wrong. But if we look at this and we try and actually use the logic, I think it's much better. So, and they give us the length, so we actually need to use that. So length is how many lambdas? How many lambdas is this? 1 lambda is from here to here, or from a maximum to another maximum, or from a minimum to another minimum, right? So if I'm starting from the middle, if I'm starting from equilibrium, and I only get here, how much of a wavelength is that? What fraction of a wavelength is
that? Would it be 0.75?
Yeah, 3/4. Yep, 3/4 lambda. It's 3/4 lambda because remember a pillow A pillow is half a lambda because it's halfway through the cycle. And then what you can see here is it's going 1/2 of the cycle of that other cycle. So this would have been a full lambda, but we only stopped here. So that's 1/4, 2/4, 3/4, and yeah, 3/4. Okay, so just visualize it. Always better to visualize it. Now that we have a formula for L equals 3/4 lambda, now we can say lambda equals 4/3 L. So now we can plug in 4/3, and L is 0.30. They gave that to us in the problem. So we can do some, you can put this in your calculator, or you can do this quickly. Let's just do it in a calculator. Okay. 340 over 4/3 0.3. I'm getting 850 hertz.
Yeah, that's what I got too.
Perfect. Now let's check the mark schema and make sure that's correct. Yep, 850 hertz, exactly how we did it. So they're going to give you 2 points just for the right answer. So a lot of time in physics, the work isn't as important. You obviously still have to do it because sometimes they do give you partial credit. But oftentimes in physics, if it's like a simpler question, you just get points for the right answer. Okay. Now we're going to deal with part B. So we have the speed of sound in air is 340, okay? And the speed in water is 1500. These wave fronts are making an angle theta with the surface of the water. Determine the maximum angle theta max at which the sound can enter the wave. Okay. The maximum angle theta max at which the sound can enter the wave. Okay, what does that mean? So that should make you think of critical angle, right? Because if it's above that angle, what's going to happen is you're going to have total internal reflection, and none of the and then what's going to happen is that this wave is going to be totally reflected back into the air. It's not even going to go into the refraction. The angle of refraction is going to be 90 degrees, right? So we want to find that maximum angle, so which is the critical angle in this case. So guess what we get to use? We get to use Snell's law. Sine theta 1 over sine theta 2 equals V1 over V2. That's correct, right? So now here's the thing. If we want that maximum theta, this is going to be theta max. That is incident. The incident is going to be theta 1, so we're going to plug in theta max here. And the theta 2, in order for us to have total internal reflection, we're going to want an angle of refraction of 90 degrees. That's going to result in total internal reflection, right? So we're going to plug in 90 degrees for theta 2. And of course, we know that sine of 90 degrees is just 1. So we can really effectively get rid of that. So we know that sine of theta max is V1 over V2. That means theta max equals arc sine of V1 over V2. Now they give us V1. V1 is 340. And V2 they give us, which is 1500. And of course, the dimensions will cancel. We have meters per second, meters per second. And you can do this in your calculator. Let's go ahead and do it. Arc sine of 34 over 150 is 13 degrees, 13.1 degrees, but I think sig fig wise, I would go with 13 degrees, or I would write approximately 13 degrees. Is that what you guys got? Arc sine?
Yeah.
Okay. Okay, now something important to realize here. Theta, the sine theta 1 that we use is the angle of incidence. This right here is the angle of incidence from the ray to the normal. But guess what? They're using theta here. So why was I able to say that that theta is equal to this theta? Well, reason being that if this ray, the angle of incidence, is from the ray to the normal, which is by definition 90 degrees, and if the ray is perpendicular to the wave fronts, that means this theta has to be the same as this theta. Just it's a geometric argument, okay? So just make sure to remember that the angle of incidence can be defined in two ways. The angle of incidence, one, is it's the angle that the ray forms with the normal. Two, is it's the angle that the wavefronts form with the surface, right? Because the wavefronts are perpendicular to the ray. That's how that logic works. Okay. All right. Let's check, make sure. We got 13 degrees, right? Yep, 13 degrees is a critical angle. Okay. Now draw lines on the diagram to complete wavefronts A and B for theta less than theta max. So we want to complete the wavefronts for A and B as they enter the water. So what would we think happens? So let's draw the normal first, because it's always helpful to draw the normal. Remember, C hasn't entered the water yet. So what happens when these refract?
It comes out, but like not in the same direction. Like
yes. Now,
it's in the same direction,
this,
but like not.
Or do you think the waves will start looking more like this?
The second one, right?
The second one, yes. Why? Because we're going from, remember, this is a sound. This is not light. If this were light, we would be going from a fast medium into slow medium. But sound, which is a mechanical wave, relies on the vibrations of the medium. So in sound, when you're going from air to water, you actually go into a faster medium. So because it's going faster, these waves, like imagine it like this, right? If a car is going like this and all of a sudden it enters a fast medium, guess what? It's gonna start turning, right? If it enters a faster medium, it's gonna start turning. So that's why you're gonna have that. But another important thing to remember here is that the distance between here to here and here to here is not going to be the same. That distance will have increased because this is close. Remember, C hasn't even entered the water yet. So as you get further and further away, the wavefront is still maintaining that same angle. So I would do something like this, just to emphasize that it's gotten bigger. I wouldn't do exactly the same, because then that would imply that this distance is the same as that distance. But that's not true, right? Because when you're going from this slower medium into a faster medium, the first wavefront is going to go, like, it's going to turn more than the second wavefront, which is going to turn more than the third, and so on and so on. It's like a kind of like a cascading effect. So I would draw it kind of like maybe something like this, like that. Maybe a little bit more like that. Yeah, I don't know. Let's look at the mark scheme and see how they do it. So on the mark scheme, they drew it like that. Okay, greater separation. That's the point. They have to be more separated than they were before. You see how like that's turned more, and the separation is greater than this from there. Do not penalize the lengths of A and B in water. That's fine. Wavefront of see if it's consistent. Yeah. Okay. Yeah. Here's the other thing. You notice like it didn't ask for C. If it doesn't ask for C, don't do C. Don't volunteer an IB. That's what Miss Raja always says. Never volunteer extra. Just do the what's asked by the problem. Okay. All right. Let's do another one. Now this is an HL problem, but I'm pretty sure you guys can do it. It's not really HL. Like I think we've covered this in class. So honestly, it could be fair game for the exam. Let's take a look. So there's this ball. Sorry, by the way, this is from a second part of a problem, so we're gonna need the radius. The radius is 8 meters. Is it actually 8 meters? That's kind of crazy. Yeah. Okay. I'm just gonna tell you because they would have given this to you in a different part of the problem. They didn't include that problem. But anyways, this R is 8 meters. So now there's a ball that's displaced from an equilibrium position and then it's released. And the magnitude of the force on the ball towards the equilibrium position is given by mg x over r, where r is the radius. Now, what can you tell me immediately by looking at this? What do you think will happen to this ball once it's released?
It's going to lose, or it's going to get slower as like it goes back, or
so yeah, that's a good instinct. What happens is as it goes down, it's going to pick up speed, and then as it comes back up, it decreases speed, and then it comes back, goes back.
Yeah,
This is essentially a pendulum. Okay, essentially this is a pendulum. Now what you can see here is that the force is mg x over r, but what's special about this? If F is proportional to X, that means A is proportional to X, linearly proportional to X. So what does that mean? It's simple harmonic motion. So when part D1 asks outline why the ball will perform simple harmonic motions, oscillations about the equilibrium position, all we have to say is that A, force is linearly proportional to the displacement, and B, this force is a restorative force. Do you see how it's saying toward the equilibrium position? Because it's restorative, those are our two conditions for SHM. We want it to be towards, it's a restorative force towards equilibrium, and it has to be linearly proportional, right? Okay, let's check the marks scheme. The restoring force, acceleration is proportional to displacement. Perfect. Okay. Now they're asking us to show that the period of oscillation of the ball is about 6 seconds. Okay, so what do you remember about the period of a pendulum? Do you remember the formula? TP equals?
Yeah, wait. I thought it was like T equals 2 pi and then square root L over G.
L over G. That's exactly what it is. No. Isn't it G over L? No. 2 pi square root L over G.
No, it's L over G.
It's L over G. Okay, I'm sorry. Yeah, I rely on the formula chart for things like this. The reason why I put a P there is for pendulum because you also have a period of a spring, and I just like to draw that distinction. Okay. Now, in this case, what's the L? The L is just the radius, right? And I told you, remember, they didn't give it to us, but pretend that the radius is 8 meters. So you're going to have 2 pi square root 8 over G, which is 9.81. And guess what? If you plug this in, 2 pi square root 8 over 9.81. Oh, by the way, here's where I would put units. I think here it is important to put units. This is meters per second squared. Meters will cancel.
Wait, G is just like the gravitational.
Yes, so it's 9.81 meters per second squared. So 2 pi square root 8 over 9.81, and we get 5.67 seconds, which is approximately 6 seconds. I would do that. Now, there's another way to do this, and I want to show this way to you just so you're more familiar with what simple harmonic motion actually is. Now, in simple harmonic motion, we know that the acceleration, if we draw it as a vector, is linearly proportional to the opposite of the displacement, right? Because it's a restoring force. So what we find actually, if we do the calculation, if we actually do a differential equation and we solve it, is that acceleration equals negative omega squared x. Omega is the angular frequency, okay? Omega squared in this case, so if F equals mgx over r, right? If F equals mgx over r and F equals ma, we can cancel out a mass from both sides and we find that acceleration equals gx over r. But guess what? This is the x, so that means omega squared has to be g over r. So if omega squared is g over r, that means omega equals square root of g over r, right? And by definition, the period is 2 pi over omega. So if period is 2 pi over omega, that would be 2 pi square root r over g, which is exactly where this formula comes from. If you don't know this formula, this is how to derive that. And oftentimes they might ask that, but I'm probably sure they'll probably just ask that in HL. You probably won't need to know that for us. But still, it's good to know that. I think it shows you where that comes from.
Wait, I had a question.
Sure.
So when you were deriving it, what did you do with the x to like when you went from the force formula to?
So F equals mgx over r, as they tell us, and we know that by Newton's second law it's ma, right? So if we divide both sides by mass, we get acceleration equals gx over r. But we know that acceleration also equals, oh, I forgot the negative sign. Because I'm dealing with a vector here, that's why I put the negative sign to the, don't worry about the negative. It's omega squared x, right? Acceleration is omega squared x. That means I can set this equal to omega squared x. So the reason I was able to get rid of the x, I'm essentially dividing both sides by x. That's what I'm doing, algebraic. Now I know that omega squared is g over r, and I know I should also be writing a over x now, but just pretend like, you understand. Okay. Okay, let's see what they did. About 5.7 seconds, which is about 6 seconds. Yeah. And so do you see here how here they actually, because this is HL, they're requiring you to actually drive it. They're going to give you 0 points if you simply just plug it into 2 pi square root L over G. Now on Raja's test, you'll probably get credit, so don't worry, okay? Don't worry about that. So that's why it's important to still know how to do it the other way. But yeah, don't worry about it for Raja's test. I think she will definitely allow you to just plug that in. Okay. Now the amplitude of oscillation is 0.12 meters. We want to draw a graph to show the variation of time with respect to velocity for one period. Now, the way we do this is first off, we start with x. X, the formula for simple harmonic motion is the amplitude times the cosine or sine. But we're going to start with cosine because we're starting from a maximum. So it's a cosine omega t, right? So that means velocity is going to be negative. This is calculus, but I don't know. I think there's probably a formula in the formula chart, so you would know how to do this. This would be negative a omega sine omega t. Okay, so our amplitude was how much? The amplitude is 0.12. They tell us that. This will be negative 0.12 times omega. Omega in the last problem, we found out that omega was what? Was square root of G over L. Yeah, that's omega. Omega is square root of G over L, as we found out in the last problem. So this is going to be the square root of 9.81 over the radius, which is 8. And we have sine omega t. Omega is, we'll figure that out in a bit. Okay. The main point of this is to realize that this is what the function. It's negative 0.12 times square root 9.81 over 8 sine omega t. So to find the amplitude of the velocity, we need to actually multiply these together. If we multiply these together, we're going to get 0.12 times square root of 9.81 over 8. And we get 0.133. So what I'm going to do, this is important because this will show me where to start the graph. Now notice it starts at a negative sign. So if it's a negative sign, function, well at sign equals 0, I'm going to start with 0, which makes sense, right? Because I'm dropping it from rest. So that means at 0 it has to be equal to 0. But now we're going to actually go down. Okay, we're going to go down and then we're going to go up. So our negative amplitude is going to be negative 0.133. This is 1, 5, 1, 1, 1, 2, 1, 3. This is about 133, I would say. This line right here. Okay, so I'm just going to draw that line as a reference line for myself. And then 133 appears 1, 2, 3. So about up here is the amplitude up here. Okay, now, in order to figure out how long, we figured out the period was how long? In the previous problem, we figured it was like 5.67 seconds, right? 5.67. Yeah. So we're gonna, yeah. So 5.246. That's 5.6. 5.67 would probably be somewhere around here. Okay. Shreya's here. Okay. So 5.67 would probably be around here. So that would be the length of one period, right? So now, where would the second 0 be? It would be 5.67 divided by 2, right? Because that's how a sine function works. The second 0 is going to be 2.837. So 2.2468. 2.837 is like right here. So what I notice is that these are my zeros, and I know that this is a negative sign. So I'm going to go down first, back to 0, and then up, and then back to 0. Okay? So the negative displacement, if I divide 2.83 again by 2, I know that's going to happen at 1.418. So about 1.4224. So about like right here, I'm going to draw a negative here. And then at about 2.84 plus 1.41, 4.25. So 4.25 right about here. I'm going to go up right here. I'm going to go up to this point right here. Okay. Now I have sufficient points to draw a sine curve. Now it's going to look like this. You would want to make it more smooth. I know I'm drawing on the computer, but that's what it would look like. Okay, so let's now look at the mark scheme and see what they said. Does this make sense what we did here? We're using the formula for velocity, and then we're just doing some math and graphing it. Okay. Yep, that's exactly what they did. So let's see, look at what they're giving you credit for. Correct amplitude of 0.13. Remember, the amplitude isn't, it's not necessarily this amplitude. The amplitude of the sine function here is the a omega, because that's what's in the velocity function, not just a. So we found 0.13, which is good. Correct period, which we showed, and only one period is shown. And here they're accepting plus or minus sign for the shape of the graph. So we could have reversed it. We could have done it going above and below. But I think this makes more sense, what we did here. Okay? All right. That's an HL question for you. Doesn't seem too bad, right? Maybe the math was a little bit harder, but it's not too bad. Okay. Now let's look at a double slit problem. This is from 2018 SL. Okay, so a pair of slits in a double slit experiment is illuminated with monochromatic light of wavelength 480 nanometers. Okay, so immediately I'm going to write down lambda equals 480 nanometers. The slits are separated by one millimeter. Okay, that means the slits, the little d, is equal to 1.0 millimeters. What is the separation of the fringes when observed at a distance of 2.2 meters? The big D is 2.0 meters. This actually, there's the formula for this in your formula booklet. You'll find that S equals lambda big D over little d. Is that right, CJ? I might have done that wrong. Let me check my formula booklet.
I think that's it.
That's correct? Okay, perfect.
Yeah.
So now you can just plug stuff in. You could just plug it in. 2 on the, you plug in 2 for D, plug in 480 times 10 to the minus 9, because it's nanometers. This is where you really have to pay attention to your prefixes. On the bottom, you'll get 10 to the negative 3. If you just solve that or plug that in. Oh, is this a, oh, this is paper 1. So you probably, I don't know if you have a calculator. Let's try and do it without a calculator. I think it's doable without a calculator. So if you have a 10 to the negative 3 in the bottom, that's the same as saying 10 to the plus 3 on the top. And now using our rules of exponents, we can kind of simplify this. So first we have 2 times 0, 0, 2 times 8, 16. So we'll have 960 times 10 to the negative 9 plus 3 is negative 6. So we have 960 times 10 to the negative 6. And if we want to put it into scientific notation, we're going to have to make it a 9.6. And what we did essentially was we did 10 to the negative 2. So we're going to need to do 10 to the plus 2 to counter that, and times 10 to the negative 6. And we'll find that that's the same as 9.6 times 10 to the negative 4, which is, oh, meters. Be careful. They're writing in millimeters. They try to trick us. We would have selected B if we weren't more careful. So now if we want to go to millimeters, right? If we want to go to millimeters, then that's the same as 10 to the negative 3, right? Milli means 10 to the negative 3. So we're going to add this 10 to the negative 4. That's the same as 10 to the negative 1 times 10 to the negative 3. So I'm going to use this 10 to the negative 3 to function as a milli. That means I'm left with 9.6 times 10 to the negative 1 millimeters. So the answer would be D then, I believe. Yeah, D.
Could you also just like convert all your numbers to meters or millimeters when you begin?
Yes, that would work as well. Yeah, that would definitely work.
Cool.
Yeah, there's lots of ways to do this. I know in chemistry you're more accustomed to doing like the dimensional analysis and actually doing that. In physics, there's more, the tradition is more to just convert everything to base SI units and then work off of that. But do whatever you're comfortable with. Just be consistent. That's the main idea. Shreya, Ayusha, do you guys have any questions? I just want to make sure we answer your questions first and then we can look at the problems.
No, I just came to see like what type of questions you guys were doing.
Sure. Okay. Okay, now also, it's you do have the formula S equals lambda D over D, but it's important you know where that comes from. Okay? It's very important you know where that comes from. The geometric proof, I'm not going to go over here because it's going to take too long, but it's in the PowerPoint and it's really elegant. It's a really nice proof. It's more of a derivation. It's a really nice derivation, but what you'll find is that if you do the graph, not the graph, I don't know what I'm saying. See, this is S. You'll find that tan theta, there's two relationships you need to remember. Tan theta equals, so S over D, And the other relationship you need to remember is that sine theta equals, give me a second. I think it's, oh my. I would need to draw it out because I don't remember it actually, to be honest. Looks like that, from there, this is D, that would be theta, this would be D sine theta. Okay, that's right. D sine theta equals n lambda. It's equal to the path difference, essentially. Yes, D sine theta is the path difference, which equals n lambda. That means sine theta equals n lambda over D. Usually we're dealing with just n equals 1, and this is why we can use small angle approximation to actually come up with this formula from these two identities. So if you're just curious, for very small angles, sine theta equals tan theta. So that means n lambda over D equals S over big D, which means that S equals n lambda big D over little d. But usually we're just dealing with path difference of 1, so that n goes away. That's where we get this formula. But it's really important you know these two formulas. And more importantly, I think if you know how to derive them, that's more like you'll be able to remember it better. So just know how to work with these, because you'll often be asked to find that value of theta. So, and they don't give you theta, that formula. So you need to know how that works. Okay. By the way, any questions on that, or are we good to move on? Cool. All right, I'm going to move on. Next question. A lot of these are multiple choice, which is good, because I think it's good to have balance between both. Okay, so sound wave has wave. I know you can see the answer. It doesn't matter what the answer is. I'm sure we can get there. More important is how we get there. So the wavelength is lambda equals 0.20 meters. What's the phase difference between 2 points which are 0.85 meters apart? Okay, the way I like to see this is I like to see this as, this is lambda. Okay, this is lambda from here to here. Okay. Now, if these 2 points are 0.85 meters apart, they're going to be a couple. Do you notice that this 0.85 is bigger than lambda? What that means is after covering 4 of these lambdas, after covering 4 lambda, where am I going to end up? I'm going to end up at 0.80 meters, correct? Okay, so I'm trying to find, essentially this is like a deal of working out remainders. So now the reason why I went to 0.80 was if I went to 5 lambda, that would have been too big. So I want to find how many lambdas I have, and then how much leftover I have. So the remainder, the leftover, is how much? It's 0.05 meters. That 0.05 meters is going to tell me the phase difference. Because essentially, it's equivalent to say I'm 0.85 meters apart and 0.05 meters apart. Because 0.05 and 0.85 are in phase, because there are multiple of lambda apart. That's what, whenever you're dealing with phase difference, you need to think in terms of multiples of lambda. So if I have 0.05 meters left over, and my lambda is 0.20 meters, what fraction is that? 5 out of 20? 5 out of 20 is 1/4. So 1/4 is my phase difference, 1/4 of the period. So if 1/4 of the period is my phase difference, 1/4 is 90 degrees, right? Because 2 pi is 1 phase. That means 90 degrees is 1/4 of the phase. You might be tempted to say 45 degrees because you think, pi over 4. But remember, don't think of it that way. The way to think of it is this is 1/4. You're essentially taking 1/4 of 2 pi, which is going to end up giving you pi over 2, which is 90 degrees. Okay? I like to think of it in terms of fractions. I know that there's probably a formula out there, but I think, once again, conceptually, you're much better. You're more likely to actually be able to apply your knowledge in different scenarios than just use a formula. Okay, any questions? Okay, I think we're good. Next one. By the way, just let me know when you're good. I'm probably going to go till 7, maybe even longer if you guys want to do more. But feel free to leave if you have to, or ask questions if there's something particular you want to work on. We can always do that. Okay, so I think we've covered a good variety. We haven't done polarization yet. That's the only thing. So we might want to do a problem with polarization. We've done, you know, Malice's law, not Malice's law. We've done this Snell's law. We've done different media. We've done simple harmonic motion. We've done a lot of stuff. So we've covered a lot. Anyways, this is from May 2018. Let's see. What are the changes in speed and in the wavelength of monochromatic light when it passes from water to air? Okay, so what happens? I know speed we can immediately do. If it's going from water to air, light is going from water to air, what happens? The speed.
Wait, wouldn't it increase?
Yeah, it would increase. Yeah, exactly, because air is
Yeah.
faster than water for light, right? So we can get rid of C and D. Now, what about wavelength? Okay, this is a matter of V equals lambda F. The fundamental understanding of this is that F is controlled by the source. The frequency does not change. The frequency is controlled by the source. So if frequency does not change and V increases, then what has to happen to lambda?
It has to increase as well.
Exactly. Has to increase as well.
Yeah.
So the answer would be A. Yep, it is A. Okay. More simple harmonic motion. Let me see if I can find a polarizer question, polarization question, because that would be helpful, I think. Oh, there's quite a few questions about that. Wow. Okay, so there's no way we're going to get through every single question here, obviously, because that would probably take ages, and we don't have ages today. I mean, you know, you can pick a few. Let's go ahead and do this problem, and then we'll go over to some polarization. Which is true about the acceleration of particle? We've already answered this question before, right? This is a fundamental question. Oh, okay, the answer is not a fundamental answer. But anyways, we know that in simple harmonic motion, the acceleration is linearly proportional to the displacement, and it's opposite the displacement, okay? But what we also do know is that the graphs of simple harmonic motion, if we start here, and that's x, the acceleration is actually going to look, it's also going to be a cosine curve, but it's going to start at a negative instead of a positive. So acceleration, is it always opposite direction to its velocity? Is that necessarily true? If we, okay, just FYI, if this was the case, V, if I were to plot V, V would probably look like this, by the way. So is it always true that the acceleration is always opposite to velocity? No, because as we can see, V is negative, acceleration is negative. Not always the case, right? If we think about a pendulum, as the pendulum's coming back down, its acceleration is its acceleration is towards equilibrium, and its speed is also that same way, right? That means acceleration and speed in the same direction. That's why it's speeding up, right? Otherwise, it can't speed up. Okay, so we can eliminate A. It's decreasing when the potential energy is increasing. If potential energy is increasing, then kinetic energy is decreasing. So that doesn't have any connection. B, yeah, and they don't really connect. Okay, proportional to the frequency of the oscillation. Is that true? What did we say? Remember, A equals negative, if this is a vector, omega squared x. Oh, sorry, omega squared x. If anything, first of all, it's not the frequency. This is the angular frequency. And if it is true, then you would say acceleration is proportional to the square of the angular velocity. So it's not C. And we can clearly see that it's D. It's a minimum when the velocity is at a maximum. Because this is a sine curve, and this is a cosine curve. And whenever sine is 0, cosine is max. Whenever sine is minimum, cosine is 0. So an acceleration will be minimum. Oh, wait. Acceleration is at a minimum when velocity is at a maximum. Oh, I guess this is not a matter of the graph. I think this is asking about the magnitude of the acceleration, not the actual acceleration itself. So you can see in the graph when velocity is at a maximum, velocity maximum means essentially, wait, what am I drawing? Did I draw the velocity graph properly? Velocity graph should start at 0. Oh, I did. This is velocity. I'm so sorry. That's why this isn't working, because this is the velocity graph. Okay, velocity starts at 0. Whenever you have maximum velocity, like in terms of magnitude, I would have written speed here. This is kind of a deceptive question. Anyways, your acceleration is going to be minimum. Reason being, because where do you have maximum speed? Maximum speed occurs at equilibrium, right? Because that's 0 potential energy, which means maximum kinetic energy. So that means if you have maximum velocity in the equilibrium, if you have most speed in the equilibrium position, then acceleration, which is linearly proportional to displacement, is going to be 0. So it's going to be at a minimum. That's why they. Does that make sense? Yeah, that was a weird question. I think they should have specified, they should have more clearly said the magnitude of acceleration and the speed, because minimum could imply something else. Okay, polarization. These are always good questions. I think this was actually on one of our quizzes, but let's do it anyways. It's a good practice. Unpolarized light of intensity I0 is incident on the first of 2 polarizing sheets. Okay. I0. It's incident on this first, and then the planes of polarizations are initially perpendicular. Okay, so theta at this point is 90 degrees. Which sheet must be rotated and by what angle so that the light of intensity I0 over 4 can emerge from the second sheet? If we want I0 over 4 here, okay, we know that after the first sheet, the intensity is going to be I0 over 2. That means to get from I0 over 2 to I0 over 4, we must have multiplied by a half. By Malice's law, we know that that half has to equal cos squared theta. Okay? That half has to equal cos squared theta. Okay. Now another thing, I'm going to actually eliminate A and B immediately because I know that I can always rotate either sheet. You can rotate 1 or 2, it doesn't matter. If you rotate either sheet, the angle between those 2 sheets will change. So that's the first thing. So I know it can be C or D. Now we have to be careful because watch. The problem is you might think if you forgot Malice's law and you just wrote cos theta, you would have probably selected D because then you would have said the theta is arc cos 1/2. But because it's cos squared theta, first you need to get rid of that by taking the square root, and then you take arc cos to get rid of the cos. That means theta equals arc cos of 1 over root 2, and 1 over root 2 is the same as root 2 over 2. So I would go with C. Is that the right answer? Yep, C is the right answer. You see how Malice's law works? Malice's law is all about the angle between those 2 polarizers. So the thing to remember with these types of problems is you always enter with I0. After the first one, the intensity is immediately I0 over 2. And then after the second polarizer is when you use Malice's law. Okay? Okay. So is this the one we did? No, we did this one. We did the 26, we did this problem. We haven't done this one yet. Okay, let's look at this problem. This is a similar problem with polarization. Beam of unpolarized light is incident on the first of 2 parallel polarizers. So they're the same angle right now. Okay, so if they're the same angle, that means all the light passes through because cos of 0 is 1. Yeah, all the, you understand. Okay. Now the first polarizer is rotated about the direction of the incident beam by an angle smaller than 90 degrees, which gives the change, if any, in the intensity of the polarization of the transmitted light. Okay. Does someone want to take a try? Okay, so the first thing I'm going to eliminate A and C because the polarization has to be different. Why is the polarization different? Because if the first one is rotated a certain degree, then what happens is you're getting a different plane of you're getting a different plane. So polarization is different now. Okay, What about the intensity? Is the intensity going to change? If they're initially parallel and I rotate this one by less than 90, for sure, because remember, one of these is like this and one of these is like this. So when they pass through, the intensity is definitely going to be different. So I'm going to go with B. Is that the right answer? Never mind. The answer is A. Okay, let's try and figure out why. So we know that the intensity is different, as we talked about that. Why would the polarization not change? What does that even mean? I'm confused by that. What does that mean? What does it mean for a polarization to change? You guys know what that means? I'm not exactly sure. Let's see. No? Okay, let's search it up. Maybe we might get an answer. Polarization change. Not polarization. Not political polarization. Okay. Guys, I think if I would ask Miss Raja, I mean, even if it's not, maybe you could ask her before the test. But if not, I would, okay, here's my thinking. I think what it means by change in polarization is the plane of polarization. Yeah, I'm not sure, guys. I'm gonna I'll text Miss Raja about this one. Here, let me send this to her right now. Okay, all right. We'll hopefully get an answer back to her. If not, I'll post in the Slack. All right, guys. I'll make sure we address that in the Slack. Okay. Let's look at this one. Here's another question about polarization. Oh, fun. We have a free response dealing with polarization. Okay. I think what we're gonna do, let's finish this free response up and then call it a day. Because I think it's been about an hour, and I think that we've covered a pretty good, vast range of problems, in my opinion. Because yeah. Did we do traveling waves? What is traveling waves again? I forgot. Oh, that's just V equals lambda F. We've done that. Yeah, we've done it. Okay. All right. So let's take a look at this. Two microwave transmitters, X and Y, are placed 12 centimeters apart, connected to the same source. Okay. What does that mean? If they're connected to the same source, that means they're coherent, right? If they're coherent, same frequency in phase. Now, a single receiver is placed 54 centimeters away, and it moves along this line AB that's parallel to this line joining X and Y. Okay. Maxima and minima of intensity are detected among several points along AB. So this is like when you have remember path difference and constructive destructive interference? So that's what this is asking about. When it says explain the formation of the intensity minima, what would you say? Anyone? When would you get a minima? Well, there's two things that can happen. Well, we know that they interfere. One option is constructive interference, one is destructive interference. When you're going to have a minimum?
Is it destructive interference?
Yeah, exactly. Destructive interference, right? So we would say that destructive interference between the two waves, between the two coherent waves emitted by X and Y will result in, we can actually just say destructive interference between the two, because IB doesn't care about complete sentences. So you can just leave it at that. Let's see if that's sufficient for the mark scheme. Because often it's not, but let's see what they want for the mark scheme. They're saying minima equals destructive interference. So see, in this case, all you had to say was destructive interference. I would specify between the two coherent waves, because otherwise, what does that even mean? But as you can see, really, you just need to have a good understanding of what's going on, and once that happens, you can get the point very easily. Okay. And you see also, you don't get points for just saying superposition. You have to actually say destructive superposition. And you can't say waves cancel either. That's very broad. So make sure you yeah, so make sure you're good with that. Okay, now the distance between the central maximum and the first minimum is 7.2 centimeters. What does that mean? So remember, whenever we have two sources and they interfere, right, they produce that pattern where you have the central maximum and then you have the first minimum. So this is the next maximum, this is the first minimum. So if this is the path difference here is the path difference here is 0. The path difference here is 1/2 lambda. That's the path difference between these 2 points. That's 1/2 lambda there. And the distance from here to here is 7.2 centimeters. Honestly, guys, I think this is an example where I would use the fringe spacing formula. Even though this isn't Young's double-slit experiment, it kind of functions like that. And here's the thing, because if we actually try and do the geometry, it's going to be way more complicated. So let's try and use the formula, because if you can see, this is 12 centimeters, which might be what? Maybe like that, and then 54. Actually, it's not, I don't know. Well, let's try using Young's formula and then see what happens. The S equals lambda D over D. So if S equals lambda big D over little d, and we're trying to find the lambda. So we know that lambda equals S little d over big D. S, they told us, was 7.2 centimeters, so 0.72 meters, times D, I'm going to leave everything in centimeters and then convert to meters at the end. So 7.2 centimeters. Little d is 12 centimeters. Big D is 54 centimeters. So if we plug this in, we get 7.2 times 12 over 54, which is 1.6. So this is 1.6 centimeters. That would be lambda. Is that correct? Let's see. Yeah. Oh, okay. Why is it 3.2 centimeters? We would get one. So it's 12. 7.2. Oh. I'm so sorry, guys. We messed up on one little thing. So we would get 1 point for this. So it's not bad. We just forgot one thing. Reason being, this isn't fringe spacing. The 7.2 centimeters is half of S. Because remember, we're going from the central maximum to a minimum point. Fringe spacing means we're going from maximum to maximum. This is half S. So if we take half of S, we need to do 2D over here. Okay. That means, okay, S equals lambda D over D. So they're giving us half S. So if we want to find S, we need to multiply that by 2, multiply that by 2. So our answer is going to be 1.6 centimeters times 2, which is going to be equal to the 3.2 centimeters. That's the answer. It's 3.2 centimeters because you have to multiply by 2. So yes, you can use the fringe spacing formula. And if you actually do the trigonometric solution with the individual path lengths, that's going to take way more time, so I wouldn't recommend doing that. But you can do that with the whole geometry. That's like a very sophisticated way of doing it. But as you can see, you just get 2 points for the right answer. And if you did it our way and you messed up or you forgot to do the 2, you get 1.6. You get 1 point. Okay. So you do get partial credit occasionally. Okay, radio waves are emitted by a straight conducting rod antenna, which is aerial. Okay, the plane of polarization of these waves is parallel to the transmitting antenna. Okay, this is the transmitting antenna, receiving antenna. These are polarized radio waves. Okay, an identical antenna is used for reception. Okay, so now we have to explain something. Suggest why the receiving antenna needs to be parallel to the transmitting antenna. Why does the receiving antenna need to be parallel to the transmitting antenna? What do you guys think? You guys have any explanations? Why would the receiver have to be parallel to the transmitter? I think this might have to do with Malice's law, right? It has to do with like if you change I would say if the receiving antenna is not parallel to the transmitter, then the intensity of the polarized radio waves will decrease according to Malice's law. Right? I think that makes sense, because if these weren't parallel, then you would have like, they're like polarizers, right? This is polarized radio waves. Let's see what they say. They're saying the component of the polarized signal, in the direction of receiving antenna is a maximum when both are parallel. Refers to Malice's law. Yeah. So there's many ways. Do you see they're accepting many different observations. You can say that the electric current is established. You can talk about the electric field. So that's more of a Maxwell electromagnetic radiation type business going on there. You can use that justification, or you can justify it using Malice's law. I think Malice's law makes more sense in this case. Okay. Now we're probably gonna have to do some math. Let's do it. This is going to be pure Malice's law. I can already tell because it's like angles. Okay. So now the receiving antenna is misaligned by 30 degrees. Okay. So the power of the received signal in this new position is 12 microwatts. Power equals 12 microwatts. Calculate the power that was received in the original position. Do you guys remember the formula for power based on intensity? What was it? Was it like intensity equals power over 4 pi r squared? Is that correct? I think so. I might be wrong. CJ, does that look right? Can you check your notes for me real quick?
Okay, I'm looking right now.
Sure. I think this was in the first or second PowerPoint, one of the two. Might have been in the third. I don't have a good memory.
Yeah, it's I equals P over 4 pi r squared.
Because it's power divided over. Okay. So so obviously we can see that power is proportional to intensity. Okay, so more intensity, more power. So we can apply Malice's law and just essentially use the proportionality there. So if we have 12 microwatts here, we know that, okay, the power that was received in the original position. So initially, what would we have? Initially, we would have P, right? If this is emitting P, and if it's parallel by Malice's law, we would also get P. However, as soon as we rotate it 30 degrees, then that means now the power is P cos squared 30 degrees, and that's equal to the 12 microwatts that they're giving us, right? 12 microwatts. So now if we just divide both sides by cos squared of 30 degrees, cos of 30 degrees is how much? Do you guys know? Cos of 30 degrees is 1 over root 2. No, it's root 3 over 2, I think. Is that correct? Cos of 30 degrees is 1 over 2, so root 3 over 2. Root 3 over 2 squared is 3 over 4. So P equals 12 times 4 over 3 microwatts, which is going to be essentially 16 microwatts. So you just use that, the fact that this comes here, rotates, and use Malice's law. And essentially it's intensity, but they give it to us in terms of power. So let's see if that's correct. I is equal to 12 over cos squared 30, which is 12 over cos squared 30. Oh, I think they're giving you credit for just it is 16. Yeah, 16 microwatts. I guess they just didn't write down the complete answer. Oh yeah, 1.6 times 10 to the negative 5 watts. We wrote an equivalent answer, so that's correct. Okay, good. One more question and then we'll call it a day, unless you have other questions. Calculate the minimum time between the wave leaving the transmitting antenna and its reception. Uh-oh, I don't know how to do that. The time from here to here. How would we do that? Do we have a wave speed? Okay, here's what I would do. They tell us the distance, which is 56 kilometers. They tell us the speed. Oh my, okay. Calculate the minimum time between the wave. Guys, how would we solve this? I can't think of something about how we would solve this. Does this have to do with power? I don't think so. I think it's minimum time. How would we do time? How long does it take to get from A to B? Oh, maybe it might be frequency. Does it have to do with frequency? Maybe. Let's see. I'm looking at the chat. All right. Bye. Okay. Let's finish it up. There's two approaches. One is distance, speed equals distance over time, so time equals distance over speed. So if we can find, we know that that's 56 kilometers. If we can plug in, if we knew the speed of, oh, whoa, wait, this is a radio wave. Never mind, we do. Okay, see, this is why you should just start off somewhere, and then if you continue, oftentimes you know the answer. The thing is that this is a radio wave, right? So by definition, the speed is c. It's an electromagnetic wave, c. So now if we know 56 times 10 to the 3 meters on the top, c is how much? It's like 9 times 10 to the 9? I don't even know what it is. I have to look at the booklet. C happens to be C is 3 times 10 to the 8. I'm completely off. 3 times 10 to the 8 meters per second. 10 to the 8 meters per second. Meters will cancel, and what you'll find is that, okay, 56 over 3 times 10 to the negative 5 seconds. What is 56 over 3? I don't know. Let's plug that in. It's 18.7. So approximately 18.7 times 10 to the negative 5 seconds, which is the same as saying 1.67 times 10 to the negative 4 seconds, right? Wait, give me a second just to confirm that. 1.6, wait, it's 18.7, 1.87. I'm so sorry. That should be a 1.87, 18.7. Yeah, 18.7 times 10 to the negative, negative 5, so that would be the same as 1.7 times 10, yeah, 10 to the negative 4. That's correct. And in terms of sig figs, they give us 2 sig figs, so I'm going to turn this into approximately 1.9 times 10 to the negative 4 seconds. That would be the minimum time between the wave, the minimum. Let's see if that's correct. 1.9 times 10 to the negative 4 seconds. Perfect. See, sometimes you just need to start off a problem, even if you don't know how to do it, and then just think about it for a second, and then you'll see a connection. Okay. You guys have any other questions? I think I'm going to call it a day. It's been about an hour, and I'm sure we're all tired. Yeah, I would definitely go back to IB if you want more practice. I mean, it's all organized by topic. Really nice problems. Really, really nice problems. So feel free to look at them, and if not, yeah, no problem, Shreya. My pleasure. Okay, all right. I'm gonna go ahead and stop the recording, and yeah, no problem. Ayusha, thanks, Chandana, for attending. Ayusha, I'll see you guys later. Bye.